I've already mentioned that the battery pack, the high voltage battery pack, must be electrically isolated from the chassis ground. We need to be able to sense during operation whether this is in fact true. And if it's not true, we need to light some indicator on the dashboard to let the operator know that there is an isolation fault, which is a potential safety issue. The procedure we'll describe here was first developed to help first responders to accidents understand whether it's safe to touch a vehicle or not. You can see the picture here on the right. Someone was having a very bad day. I don't believe anyone was seriously injured in this crash, but that there is a Tesla Roadster. And if I remember the article correctly, it was rear-ended by this minivan, and that shoved it underneath this other vehicle. And none of them turned out looking to be in very good shape. But this Tesla Roadster has a very large, very high voltage battery pack, and if you were an emergency responder, what would you do? How would you know if it was safe for you to open the door or to pull the occupant out of there in case there was some it looked like there was some danger of them remaining in there. So that's why the standard was developed. That's not how we're using it. We're using it during operation to let us know if the battery pack is safe, but the same method applies. So the question is safety. Is it safe to touch a battery terminal, either the positive terminal or the negative terminal, and the chassis ground at the same time? So one hand touches one, the other hand touches the other. Well, in our design, they are electrically isolated. They're not connected to each other. And so the battery should be completely isolated from the chassis ground, and there should be no problem. However, in this accident, can you guarantee that that's the case? Because the battery pack is cracked, and who knows what's shorted to what inside of there. So in that situation, this is not a normal operating condition, and so we can't guarantee isolation. In fact, we have to test for it. And even during normal wear and tear of a vehicle, it should not happen, but it could happen that for some reason, some wearing in the battery pack causes the isolation to be broken because for some reason there's a crack in the pack and there's a connection to the chassis or who knows what. There could be any number of reasons, and we just want to make sure that we do have isolation. There is a standard, a federal motor vehicle safety standard, says that isolation is considered to be sufficient if you touch a terminal of the battery pack. In fact, you do a dead short between either terminal of the battery pack and the chassis ground, and less than 2 milliamps of current flows. That is the idea. It's very difficult to kill yourself with 2 milliamps of current flowing. More than that, it gets progressively easier to kill yourself. So we say, okay, we think 2 milliamps is the safety limit, and that's what we're going to use as our criteria. And the FMVSS standard also tells you the procedure for measuring whether this isolation is good enough or not. However, the specification does not give the derivation. And the derivation is not difficult once you see how to do it, but it did take a couple of graduate students and myself several days to kind of reverse engineer how the derivation was done, and you're going to see it takes just a couple of lines, and it's not that hard. But we had to figure out what is the circuit that they are assuming first, and this is what it is. So here I have the high voltage battery pack and its positive and negative external terminals, and here I have the chassis ground. And during normal operation, they are completely 100% disconnected from each other. There's just no connection at all. We draw in these resistances R1 and R2. Now, ideally, these are infinite, or they're many mega ohms. It's, this is the resistance, electrical resistance of all the packaging of the battery pack between the battery and the chassis ground. So the battery is somehow bolted to the chassis, but there's a lot of insulating materials in between. So we would imagine that R1 and R2 would be nearly infinite or almost immeasurably large. However, if I have a fault on either the low side, the negative side, or the high side, the positive side of the battery pack, then R1 or R2 will not be infinite. They will have a less than infinite finite value. And in order to figure out, well, what value of resistance is okay, we take the specifications of 2 milliamps of current flowing, and we say voltage divided by current is resistance, and so the battery voltage divided by 2 milliamps gives you this weird relationship. 500 VB is the numeric value, but it's measured in ohms because 500 is in fact 1 over amps. So the minimum resistance, isolation resistance of R1 or R2 is 500 times battery voltage. So if the battery voltage is 100, then 50 kilo ohms would be the minimum resistance. So our goal is to define a procedure to measure R1 and or R2, to measure the minimum of those, in fact. And if the minimum is bigger than 500 VB, we are okay. If the minimum is not bigger than 500 VB, then we have an isolation fault and we must inform the user of that. So somehow I need to measure the isolation resistance. The isolation resistance is the minimum of R1 and R2. I don't care what the maximum is, I care only what the minimum is. I need to measure Ri somehow. What we're going to do is a two-step process. The first step is I'm going to measure both the voltage V1 and V2. So V1 is the voltage between the negative terminal on the chassis, and V2 is the voltage between the positive terminal of the battery and the chassis. So to measure a voltage, I need to use a voltmeter, essentially, an analog to digital converter. And an analog to digital converter draws some current. It has some resistance. So that means that to measure isolation, I actually have to break isolation because I am inserting into the circuit these two voltmeters, which are breaking isolation. So I have to ensure that whatever voltmeter I place in there has a high enough resistance or impedance that its resistance is going to be much, much, much bigger than 500 VB. And so the specification says to insert a high impedance measurement circuit with at least 10 mega ohms of impedance for V1 and for V2. So again, this breaks isolation, strictly speaking, but that's not enough to worry about. And also note the polarity of the voltage readings here, the plus minuses. They're oriented in such a way that the voltages are always positive. The voltages that are measured are always positive. So the voltage V1 is going to be equal to, because V1 is in parallel to R1, that's equal to the voltage over R1. And V2 is the voltage over R2. And so we know that voltage equals current times resistance. And because this is really a current loop here, the resistors have to be experiencing exactly the same current from each other. So the one that has the highest voltage is also going to be the one with the highest current. And basically what I have here, if I redraw that circuit, is I've got the battery, and then down here I've got R2, and then down here I've got R1. And you can think of this as if I thought about, the chassis is right there, and I'm measuring these two voltages here. Basically, I'm making a voltage divider with R2 and R1 across the battery. And the smaller resistance is going to have the smaller voltage drop. and I want to know what the smaller resistance is. So if that's the case, I want to find the smaller of the two. So if V2 is bigger than V1, that means that V2 is next to the bigger resistance. I actually want to find the smaller resistance, so I need to find R1. I need to solve for R1, otherwise I need to solve for R2. So after the first step of finding both V1 and V2, I go to a second step that depends on whether the first step had one result or the other result. Before we go into the second step, we'll note that I1 equals I2. Again, it's this circuit here. I1 and I2 are the same. And V1 over R1, which is equal to I1, has to equal V2 over R2, which is I2. And we will substitute this identity in the derivation. So suppose we've decided that the lower voltage is V1, so that means that R1 is the lower resistance, and so that's the one we need to worry about the most. I need to solve for that. Well, I need an independent measurement to be able to solve for R1. And what we do is, once again, we intentionally break isolation. In this case, what we do is we insert, using a transistor switch, a known resistance R0, not on the R1 side, but on the R2 side. And this known resistance R0 must be big, because we are breaking isolation. We can't allow more than 2 milliamps of current to flow. And so the R0 must be big enough to enforce that. So R0 must be much bigger than 500 VB again. But what happens is I put R0 in parallel to R2, and that parallel resistance is different from R2, so I have a different circuit. And I'll have basically a second equation. So I have two equations, two unknowns, and by inserting the known R0, I should be able to solve for the unknown R1. I measure the voltage a second time over here, and I call this V2 prime. Prime simply indicating a second measurement, not that it's a derivative or anything like that. And then we evaluate this circuit. The current flowing through this resistor must be the sum of the current flowing through that one and that one. So on the right-hand side, the current through R2 is V2 prime over R2. Current through R0 is V2 prime over R0. On the left-hand side, the current is equal to the battery voltage minus V2 prime. That's the voltage drop over R1 itself divided by R1. That's Kirchhoff's current law tells us that. We know that the battery voltage is equal to V1 plus V2, the previous measurements, and that R2 and R1 are related to each other by this equation right there. I'm just using that. So I substitute those in. VB becomes V1 plus V2, and R2, not yet, but down here, becomes this R1 divided by V1 divided by V2. So with those substitutions, we have an equation here where all of this equals all of this. And we look at it and determine what do we know. We know R0 because that's our designed resistance that we put into the circuit. We know V2 prime, we measured it. We know all of those voltages. We know all of those voltages. All that's left is I have R1 on that side and R1 on that side, and that's what I'm trying to find. So we do a little bit of algebra to solve for R1. It's not difficult. We bring all of that over to this side of the expression. So V1 plus V2 minus V2 prime is that, and then I'm subtracting out this, and then divide by R1 equals what's left over is that. And I do the 1 over both sides of the expression and solve for R1, and I get the given equations that are there. So I can evaluate this. This is the form that's actually given by the standard. It's factored in that way. But this is the short derivation of where that equation comes from. So once again, to measure isolation, I first measure V1 and V2 on both sides of the battery. I insert the R0, and then I measure V2 prime. I do this calculation. That gives me R1. R1 is the lower of the two resistors. I have no idea what R2 is, but I don't care because I know R1 is lower. And if R1 is bigger than 500 VB, then I have isolation. I'm okay. But if it is not, I do not have sufficient isolation. It's not okay. Now, suppose the problem was not R1 but R2, then I would find that V2 was the smaller of V1 and V2 in the first step, and so I have to do somewhat different operations in the second step because of that, but they're the same idea. There's no difference in the idea. So I'm trying to find R2. I know this here is the potential problem. It's worse than R1. I insert intentionally R0 on this side now, on the R1 side of the expression. And again, R0 must be big enough so that I'm not breaking my isolation standard by inserting it. And now I measure a V1 prime. And by Kirchhoff's current law, again, the current flowing through this resistor must be this current flowing through that one, plus the current flowing through that one. So on the left-hand side, these are the two currents that are flowing. On the right-hand side, that's the current that's flowing. I know that the battery voltage is V1 plus V2. I can replace R1 by R2 times V1 over V2. So the expression is written in terms of the measured voltages, the known R0 resistance, and the unknown R2 resistance. I follow the same kind of algebraic steps to bring R2 to one side of the equation and simplify, and we get this result right there. So again, if I measured that V2 is lower than V1 in the first step, R2 is the possible problem, so I need to solve for R2. I insert a known resistance R0, I get an additional voltage measurement, I do this computation. The isolation is considered okay if R2, which is the lower resistance, is bigger than 500 VB, and it's not okay otherwise. This is done frequently, maybe once a second while the vehicle is in use, and just in order to continuously know what the isolation status is. A second topic in this section gives us our final sensing and high voltage control requirement for a battery management system, and that has to do with thermal control. And this is certainly not my specialty area, so I don't go into it in detail at all in this course, but it is a very significant design concern of a battery management system. In fact, the thermal controls on a Tesla Model S car, for example, are probably more sophisticated than the battery controls are. And the thermal controls on the Chevy Volt are extremely carefully designed in order for basically to keep the vehicle safe and to keep the cells healthy as long as possible. So I'm not going to go into this more than this one page of notes. I did notice, though, that some colleagues of mine have written a book. It's published by Artec House. It's coming out this quarter. It's already available on Amazon for pre-release. So if you're interested in thermal control, you might look up the authors Santhan Gopalan, I think I spelled that right, Sriram Santhanagapalan, and Candler Smith. They wrote a book published by Artec House, A-R-T-E-C-H, on battery management, and it sounds from the synopsis that I saw that it has a lot to do with thermal management, and that is their specialty. They work at National Renewable Energy Labs in the thermal management area. They do a lot of battery work. Both of them come from very respected schools that work in battery systems, chemically speaking, but the NREL job that they have now focuses a lot more on thermal aspects and modeling. So that looks like a good book if you want more information. I can't give it an endorsement because I haven't read it, but it looks like it's probably going to be the thing you want. The picture on the right tries to show the operating window of a lithium-ion battery cell that is safe. And in voltage terms, somewhere, it depends cell to cell, but somewhere between, say, 2.5 and a little over 4 volts is usually safe for lithium-ion cells. And in temperature, maybe somewhere between about -30 and plus 50 or 60 degrees Celsius is a safe operating window. Now you might want to operate not at the edges of this, more in the center, because that's certainly not at too high a temperature, or probably not too low a temperature, and maybe not too high or too low. So you can decide what is considered safe. There's one issue of safety in terms of is the cell going to catch on fire, or there's another thing of will the cell last for a very long time. So if you want the cell to last longer, you have narrower operating window limits. The chart, though, shows some of the things that happen if you start operating outside of those limits. So if the cell voltage gets too low, the current collector on the negative electrode, which is usually made out of copper, will start to dissolve. And so you've got these copper ions floating around in the electrolyte, and they try to behave like lithium ions. They're both positively charged, except the copper ion doesn't really intercalate, and so it causes metal plating on the electrodes and starts dendrite formation and so forth. So it will eventually short-circuit your battery cell, and it's not a good thing. At high voltages and low temperatures, we start lithium plating during charge. I've mentioned that before a number of times. So that's not a good thing either. You lose capacity relatively quickly. We have dendrites forming, again, possibilities of short circuits. At high voltages and high temperatures, the positive electrode active materials can actually start dissolving into the electrolyte, and you start losing capacity. And the chemical constituents of the positive electrode can try to cycle like lithium does and end up contaminating the negative electrode and so forth. So that's bad. We want to stay away from too high voltages. And at much higher temperatures, you've got things like the solid electrolyte interphase layer on the negative electrode breaks down, and then new SEI forms. You have very rapid capacity loss. We also have, at higher temperatures, the electrolyte is breaking down in an exothermal reaction, which means that it's releasing heat while it's breaking down, which generates more temperature, and you end up with releases of flammable gases, and pressure increases, and the separator melts, and then you have short circuits, and the gases might build up enough pressure that you vent these gases into the atmosphere, and some of them are combustible, like hydrogen gas is one possible outcome, which is combustible. And because of this exothermal breakdown, the temperature, once you reach a certain point, becomes self-sustaining, and you have what's called thermal runaway, and the cathode active material breaks down, not in the sense of dissolving, but in the sense of oxidizing, basically catching fire. And there's enough oxygen, the cathode materials, the positive electrode materials are usually oxides, and there's enough oxygen in them to maintain any kind of combustion that has started. So even if you completely smother the battery cell at that point, there's enough oxygen internal to the battery cell to maintain a fire. So at this point, if you ever get here, you hope you don't, but if you ever get there, the fire extinguisher is only going to put out the secondary fires. It's not going to put out the battery fire itself. The battery fire is just going to run until there's nothing else left to burn. So we don't want to get anywhere near there, and so we want to stay in the safe operating window. And as I've mentioned before, if you feel comfortable, then the battery is probably at a safe temperature. And if we keep these cell voltages within a certain range, it's probably safe as well. Although in Chapter 7 we discuss some refinements to that thought process. So how do we keep temperature in a range that is safe and also allows for a long battery life? One possibility is to use forced air cooling. So I've got a battery cell, and I force air over it using a fan. And air cooling might be sufficient, especially for electric vehicles. Probably not sufficient for most hybrid electric vehicles, although in some cases it would be. Now, that might seem backwards. You're thinking electric vehicle, big battery pack, isn't that harder to cool? Well, electric vehicle has a big battery pack, but the power we're using from the battery pack is relatively small because I need long range. So if I want to have a, say, 300-mile range in my battery pack, I might have 85 kilowatt hours of capacity, but I'm only using, I don't know, 50 kilowatts at a time. So I'm using less than a 1C rate for the battery pack on average, which doesn't stress the cells very much. But for a hybrid vehicle, I'm really concerned not with energy to drive a long distance, but with power to get that energy out quickly, which means that the C rates are much higher. And we're talking potentially up to 30 or 40 C in a hybrid electric vehicle. At least we've tested things up that high. I don't know if anyone's actually implemented that on the market yet. But because of that, the relative current flowing through a hybrid battery pack is much greater than the relative current for an electric vehicle. And so that's why you might be able to get away with a simpler cooling system for EV. It's my understanding that the Nissan Leaf uses air cooling, whereas, for example, the Chevy Volt, which is an extended range hybrid electric vehicle, uses liquid cooling. So that's the second one, liquid cooling. Again, I've got a battery cell, and instead of air flowing across it, I have some heat exchanger maybe between it and the next cell. That's how the Chevy Volt does it, where I put liquid, through this heat exchanger, and the liquid carries the heat away. Liquid has a higher coefficient of conductivity than does air, so it's a much better material for pulling heat out of some hot system. Evaporation is even better. I don't know anyone who's even thinking about using evaporative cooling, but if you have an extreme case, you can do that. Basically, you would squirt some kind of a phase change material onto the surface of the battery cell, and when the material evaporates, it dramatically cools the battery cell in the process. So that's why your pores sweat. The evaporation is what cools you. So that might be necessary in the future. I don't know. The more complicated the thermal management system is, the more expensive it is. And so the automakers try, whenever possible, to get away with air cooling. And if that's not enough, then they resort to the liquid cooling. Sometimes heating may be necessary if the battery pack is too cold. And it's a little bit redundant, because imagine a battery pack which is sitting at maybe minus 10 degrees Celsius. When you use the battery pack, it has some resistance, and it develops, current and resistance. There's heat generated. So simply using the battery pack heats it up. We have an I squared R kind of heat generation, which changes the temperature. So the cold operation case for a battery system really pertains mostly to the startup process, the first few minutes of driving, because after the first few minutes, the battery pack has self-heated to a comfortable operating regime, and after that it has to be cooled. But if you want optimal kind of vehicle performance, and if you can plug your vehicle in, you might consider having heaters as well. The heaters could keep the battery cells within your safe operating window. For example, if you want to charge the battery pack, you might want to heat it so that you avoid the possibility of lithium plating. And then you'll have a battery system also that's ready to just work at full operating capacity right away when you turn the vehicle on. It doesn't have a warm-up period to it. So that's a design possibility, and the Chevy Volt does do heating when it's plugged in, if it decides that it's necessary. And finally, if you are concerned about modeling the thermal behavior of your battery system, you probably want to measure the input and output temperatures of the coolant that's used, whether it's air or liquid, to use with your thermal model to give you some idea of how much heat is being generated by the battery pack overall, and see if that corresponds with the temperatures that you're reading. If it doesn't, it means that heat is being generated somewhere that you're not measuring, and that's a concern that you'd probably want to know about. So that ends our considerations of the sensing and the high voltage control. And now it's time to move on to some of the other requirements that we listed in the first topic for a battery management system.